Hey everybody, Brian here from quantlabs.net. Just wanted to go over this potential. I don't like to really use the word potential. High frequency trading architecture considerations using Fastflow with C++. Now, this is a multi-threading, multi-core framework. I'm not going to go over what it is. I've got a video playlist for that. So we're now working off of a recent release of Fastflow 2.1 whatever. So there's some enhancements to this, and this posting is just some of the considerations I want to go over to share with people that may be of interest. First, when I say high frequency trading, I would probably guess that's a pretty close accurate statement. I say that because when you look at Fix number 8, the project uses Fastflow in their architecture as well, and they claim to have a very fast Fix framework that competes with some of the higher end Fix protocols. So with that in mind, I just wanted to show you that this Fastflow is probably as good as anything else you can get there without having to hand code the equivalent in C++. That's why I'm using it. So let me go through a couple of things. First, I'm making this video so you don't have to read my potentially bad typing, which I'm very well known for. Also, what I'm going to show you is from the tutorial, and I'm also considering Redis as well as part of the factor for a potential architecture. I'm not going to do any documents or anything. I'm just going to do some verbal stuff, just easier for me. Also looking for opinions as well, but by the time some people may have feedback, it may be a little too late. So this is just for those that are responding once this video has been created. So anyways, we have here, as I said, this multi-core parallel programming framework in C++. It's open source. The thing what you need to realize is with Fastflow, which is this one in the dark line, is that it's very fast. It keeps up to pace. With the short term, it's beating OpenMP, and it's keeping up to pace with it over the long run. So it's an excellent framework, and on top of that, it's really easy to work with. You don't have to be an intelligent person to really figure out how to use it. Well designed. Okay, so now that we got that out of the way, in here when you download, there'll be a tutorial, and that's the document I'm going to be focusing on. All right. So I've got a posting I've put up on my blog, which is this one here. HFT architecture considerations with Fastflow. I'm going to go through these each point by point, and I've got a Word document that's the exact same, and here it is. Okay, so let's get to it. So as I said, just download the source code. You can do an easy build. There's instructions on how to do that. I'm not going to do that. But this document I'm talking about is the FF tutorial. Now let's go through section by section. This is the document, so we're looking at page 14. Okay, all right, so first thing to consider is node management. Now, node management is essentially workers. So if you're doing anything in parallel, you're going to be using this a lot. And those are your equivalent of nodes or workers in any parallel environment. Now, if you go to this figure here at 3.3, let me see if I can find it. This guy right here. Figure 3.3. We want right here. Okay, this is how it works. If you're going to use these different patterns, farms. There's farms plus feedback. This is just one of a few patterns that you can use within Fastflow. So here we have an emitter, and that emitter basically will send out a bunch of workers. And you can see that through the code. I'm not going to go into very much detail, but to really understand the detail of it, just read the tutorial. Now, there's many different forms you can do. So you can set a emitter that will send out various workers. Everything's divided up into stages. So you can have different stages for each worker that does separate tasks. At the end of it, once the work has been completed by all these workers, there's another task or a collector which will go through all the collected information from the various workers. From there, which this one is probably really good, is let's say in the world of trading, you have a stream and you want to process a set of algorithms on each stream, and at the end of it, you want to make a trading decision. So that last in the collector, you could have maybe some trading decision based upon your set of algorithms that you're running as a separate node or worker. From there, there is some examples here. So we're just on this section right here. Going to page 20 now. So we're looking at farm 2 as the example. So as I said here, we have stage 1, which is, let's say in my case, if I'm pumping data from, let's say, the interactive brokers Java test client, and I'm pumping data or pushing data into a Redis instance of a server that's running. What you'd want to do is you want to have your C++ stream that data into one of the tasks. So that's stage 1. Stage 2, you could have various algorithms running in parallel as a separate task or worker or node. From there, in the collector, you can make a trading decision based upon the results of your various algorithms, and we can use each algorithm as maybe a metric. So let's say option data is a really good example. Option data comes in from Redis, tick data. You run it through a variety of algorithms. So let's say you want to do some Greek analysis, some statistical analysis in each algorithm. Run them in parallel, no different than you would have like a genetic algorithm, and then collectively, based upon the results, you can make a trading decision on that. That's just one example. So here you could use that as an example. So each stage would represent all those steps. Stage 1, your input data. Stage 2, running various algorithms in parallel, and then collectively, make a trading decision. Enter the market, exit the market, so on and so forth. So that's just one consideration I'm looking at. Now, you're asking what's an emitter. Now, these are all defined on page 21. Better examples here. So I just want you to understand that. Now there's other examples I think may be useful. No collector with a main memory or send them to the next stage. So basically what I'm saying here is page 22. Let me just jump to that code here. So in this case, we could keep it really simple. We have our emitter, which is our data input being pulled in from Redis. And then we have your various workers. Last stage, we could have that trading decision based upon what the worker results are for each, call it algorithm, or metric. And that's one possibility of a design pattern. So let's see if that's farm 4. Yeah, so this would be a typical example in the hello farm 4 example. Okay. Now, there's something I really like here, the feedback channels. This is pretty cool. Here's my page 35. All right, so what we're talking about with the feedback, my feedback channels. Oh, I'm sorry, 27. Jumped a bit there. Okay, feedback channels is what we want. Okay, so what are we talking about here? Now, I want to highlight here in, I guess not. Okay, so feedback channels is basically, you have your stage 0 or your stream, you have some kind of a scheduler. So what you could do is, this is really cool. So you can have one algorithm and a second algorithm running. And as the algorithm may reject something like a hypothesis test of some kind statistically and rejects what it sees, through the feedback, it could reject it, but you could do all this parallel with other algorithms. And maybe another algorithm may pass. So you could use those feedback channels. And here's an example of that through this feedback example. That would be the same thing as probably as a genetic algorithm. But again, you got to remember, this is done in real time as you're streaming data into your into this environment of Fastflow. That's another example. Now, it gets even better than that. This thing's mind-blowing what you can do with it. So now we can combine a Fastflow task farm with a pipeline. Now, if you know me, the pipeline is a fast way of just, again, streaming data. And there's so many examples here. Figure 3.4. Let's find that. So here's a complex one right here. So you can see all these different combinations of different possibilities in terms of patterns. Emitter, worker, and so on and so forth with each one of these. Really powerful. But again, I'm still trying to figure out how to design the workers and each task. For now, obviously, it has to be hard-coded, but there may be other ways to get around that. Okay, this is where it gets even more interesting. 3.7. Now, there's a section here called Software Accelerator. That's page, I'll just, and here, page 3.7. Okay, we want this section here. Okay, so there's a line in here I want people to okay. By analogy with what happens in GPU and FPGAs to support computations in the main processing unit, the cores used to run the user-defined tasks through Fastflow define a software accelerator device. This device will run on spare cores available, so you don't have to worry about hand coding what core you're working with. This is the beauty of using something like Fastflow. And then where's the offloading? And you can offload it. Yeah. So this is no different than how a accelerator works. And again, you can use a pipeline with a task farm combination of this pattern as well. So just depending upon how you code it up. That's really powerful. I'm going to tell you, that's how basically the FPGAs work, or GPUs. But GPUs are no good in real time because they'll collect data, but then that's on the CPU, but then you also have to transfer it onto the CPU, to the GPU, which obviously takes transfer time. So you want to use more like an FPGA kind of style, but in there somewhere there is an offloading capability. So you could let the main cores do the collection and then have another set in your code to offload it to do the tasks. You can properly manage that. That is a really, really nice feature of Fastflow. Yeah, right here. So the skeletons must be started as a software accelerator and tasks have to be offloaded from the main program. So this is in the accelerator CPP. I think it's just right here. So here's a demo of that. So in my case, an 8-core CPU, this can be done in real time. So you have your emitter, have your workers, and your collector, but you can map each of the workers into a separate GPU or CPU. So if you have a high-end server, like a 16-core or even an 8-core, that can be really powerful design pattern. And that's true HFT, all done nice and easy. Now if you use a Linux with minimal services running in that background, so it doesn't take away cycles on your processor, all your effort on the processor can be put towards this design pattern in your code, and you only really run that at the OS level. So that is really good. Okay, so we have that as one example. And we have 3.6. Where's 3.6? I think we just looked at it. Figure. Yeah, so there's another combination somewhere in here. Here we go. So again, these are different demo examples you can use. In this case is using a disk, using Magic to do compression on a photo or whatnot. So that's what this is really referring to for image filtering. So we'll go through that. But again, you can do all this in memory. As long as you have the memory and you have the access, that's pretty far out. I was like, oh my God. Okay, moving on to page 40. Let's see. 40. Okay, so now there's another example here using reduce. So here we're scheduling. So we have a stream and we have a scheduler. In this case, these are the tasks, so we can run the same task in parallel to process the stream as fast as possible. So you can imagine if you have, I don't know, a big rolling window of data on a time asset, on a time series. You can run those same algorithms or strategies in parallel and get your result at the end. That's similar to what I'm looking at. That's what I'm thinking. All right, so here's for fastest processing. What we need to look for are the words stateless. The reason I'm saying stateless is because it's less memory being processed. If you're just trying to work with a stateless type of template, like I've been looking at in generic or template programming or meta programming, you want stateless. Less state managed, the faster it'll be. So let's take a look at page 44. Now here's a key word with Fastflow, data parallelism, like, hello. Okay, so here, the stateless is fully explained somewhere in here. It's one of these loops. If you like me, I think this map is the one. It's somewhere in there. But you have different types of loops. You can do mapping or loop parallelism. Here's an example of the parallel 4. Now, I've been playing around a lot with what MATLAB offers, par 4. This, with the amount of functions that you get in this par 4 class, I believe it's called, yeah. The par 4 class, you have a lot of control of how often you want to iterate through the looping or the iterating. It's quite good. But I'm not going to get into that. Actually, one example is 48, page 48. Okay, let me just show you this. page 48 here with parallel for reduce shows how to use math routines for doing summaries like an array. So here, this code right here is an example of that. How to run a large data set you get and do a summary on it. Also, I believe FFmap. Where's FFmap? Here it is. In here, right here. This is similar to multi-GPUs or FPGA. Okay, so you can get the same capabilities as long as you have a decent server, high-end server. You can do some pretty powerful stuff. And for the same price, I don't know, but it all comes down to design patterns. But this example here is a demo of that on mapping. And then we move to page 52. Where am I? So here is one example. So what we're doing is we're just doing matrix multiplication. So you have, in this case, I think there's two double arrays that you're working with, and you're going to multiply them together. No different than in MATLAB. And this is really good for whatever examples when you want to get into the quantity stuff. But again, you will have to do all that in C++. So for instance, to do this in Python, or it's not possible because it's single-threaded those. And yeah, maybe you can play around with some GPU stuff in the back end, but why go through the pain of that when you can just do all the algo development and math stuff in C++ and have C or Python and R front ends call the C++ libraries that you develop. Okay, and there again, there's another example of dot product as well. Okay, so there's that. Okay, so I just want to show you page 53. Oh, this is a Mandelbrot fractal. I've heard a lot about fractals in quant type of trading. It's an example you can use as a multi-threading way to do it. A little too advanced for me. In here you'll notice you can do lambda functions, mapping a lambda. I mean, they're just introducing that into Java, and but here you have full control over that in the C++. One thing I'll give .NET is this lambda is pretty powerful than .NET, but doing it in C++ using this multi-threaded framework is just powerful in itself. Last example to go over is the this Sobel filter. As you can see, it'll just filter out whatever. No big deal there from my end. Okay, now this is where it gets really exciting. Okay, if we move on to page 60, I'm going to talk about more from an industry point of view, the secret sauce of Goldman Sachs. Okay. Now, for those that don't know, I'm studying this, and if you are with Goldman Sachs, I know what you're up to, and I can replicate it. Goldman Sachs has an internal risk management database called SECDB, okay? And I have confirmed that it's using graph searching as its back end to process that. Now, if you have an entire C++ system written with algorithms and data coming into it from, let's say, Redis, or maybe even streamed directly in from Interactive Brokers, if I can actually do that, but that's another topic. But the point here is, if you have Goldman Sachs using this database, and what I'm about to show you, you can kind of replicate it in Fastflow. Here we go. Okay, so we are on page 60. There's this data skeleton called FFMDF, okay, macro data flow parallel pattern. So what we're doing is we have our pattern searches that we can use for different conditions. Typically in Goldman Sachs, these are various algorithms that are used for risk management. And I do know this is a policy for the SecDB. For any type of trading that is going to be opened up or put on from Goldman Sachs has to be run through the SecDB to ensure it is within compliance on an enterprise level of Goldman Sachs compliance. So this methodology is the same as this SecDB, and it's fast. So if you design this potentially as proper, as similar to how the SecDB works, you got yourself a friggin' awesome system. If it's done smartly and you got the same set of really powerful rules that Goldman Sachs uses for, again, risk management. So you could use as part of the methodology as part of complete multi-threading environment. So this right here is looking at all the different graph tasks. This right here is an example of that, okay, in Fastflow, okay? And again, I gotta remind you, it's done in a lightweight, open source, multi-core framework in C++. And I just showed you that chart. You saw how fast it is compared to Open MP. I think it's called, I can't remember the name of it. Yeah, let me just see that. It's called OpenMP, Silk, TBB, forget it. But OpenMP is definitely the right choice. Wow. Okay, so let's get back to our... So for the graph searching, that it would be an amazing capability. Now, if you really want to get sophisticated, and no language can do this other than really C++, and you can only really pull it off smartly, is doing these block multiplication. It says 63, which I believe is this example right here, this block matrix multiplication. So you're using the capabilities of the graphs, the graph search capabilities. So this demo does exist. So you can see the limitless possibilities here using this virtual framework in software. Get FPGA-like performance using Redis as the data store. And I think the key behind it is you got to have a really good fast server, a lot of memory on a minimal latency-free OS Linux distribution. On top of, you have to code it right, and you have to ensure that you're implementing the strategies at the highest performance, as well as ensuring your algorithms are high performant as well. So you can't really put in a lot of mathy stuff. So I wanted to create this for you just so you can get an idea of the direction that Fastflow will bring using this framework for multi-threading. And there's nothing else like it that I've seen comparing other libraries as well, including OpenMP, Silk, and TBB. So yeah, really important stuff. I thought I'd just put that out there, and let me know what you think on Facebook, Twitter, whatever. Talk to you later.